So we're going to be continuing to talk about limits at infinity today. The first half is we're just going to be kind of refining some of the things that we already know. And then towards the end, I want to focus specifically on limits at infinity with trig functions. And I'm pretty sure L'Hopital is going to sneak his way in there once or twice. We'll see, though. We'll see. All right. So that's our topic. Tomorrow, I will not be here, but I will not be leaving you with nothing to do. It's going to be a video lesson. I'm going to make sure it's on my desktop and not on the internet so the sub doesn't miss it again, because we just cannot be affording to take days off. So we've had, what, 2 field trips this week and all kinds of nonsense coming up. So I just don't take days off if I can help it. So I'm going to leave you guys with a video lesson, and I don't mind. I'll just be chilling at Mathlete. So if you guys want to, I don't do anything there. So if you guys like, Bailey, what's this mean? Shoot me a text. I'll answer it. Share the love with your neighbors. It'll just be like a normal lesson. You just have to talk to me through your mind if you got a question. That's the only difference, okay? But I honestly don't think tomorrow's lesson will be that hard. After this lesson, I think it'll be pretty chill. You do want to start getting prepared for your tests. I'm going to upload the study guide. Remember I gave you guys that buffer day was Monday, Veterans Day. So, you know, you deserve a rest. If you need to rest, take a rest. But that's a great opportunity to start getting a head start on preparing for your test, okay?
Oh, yeah,
So, no. So this weekend's a 3-day week, which means I would have done a Saturday school to prep you guys for your test. That's what this is like a perfect opportunity for that, because the test is like right away after this. But they don't do Saturday schools on holiday weekends, so we don't do it. Sorry, but we're gonna make do anyway. So here we go. First of all, let's talk about some basic properties of infinity. Things that we've already. This is something we've already talked about, and I don't think you guys are gonna have any qualms with this. Let's C be a real number. I'm going to be putting the letter C in here and just represent the constant, a number, okay? So for instance, this, if I told you guys, what is infinity times C? What's the answer? Now, this is bad math, by the way, bad math writing. So the only reason I'm doing this is to help you guys understand concepts without trying to take up 10 boards worth of space to communicate something you can communicate very easily. Okay, you're not supposed to say something equals infinity. You're supposed to say goes to infinity, just so you know. But I'm going to write this. Next, what do you guys think infinity times a negative C would be? It's still infinity, but it becomes negative. Okay? C. Or third polka dot. What would infinity plus C be equal to? It would be infinity. How about infinity minus C? Same thing. If you add a certain amount to infinity or take a certain amount of infinity, you still have infinity, right? Part 4. What if we have C plus infinity? What would that give me?
Same thing.
It's just infinity. What do you guys see how much I like this? All right. What do you think C minus infinity would be? Careful. Negative infinity. If you take a number and you take infinity away from it, you end up way on the left, infinitely far. So that would be negative infinity. So that one's a little bit different. How about, by the way, I think I made flashcards for most of these on that flashcard set that I put on Google Classroom. I mean, a lot of these are just obvious. There's a couple that aren't, though, and they're on the flashcards. I think they're obvious, but if they're not to you, that's okay. That's why I'm writing it. So, what do you think infinity plus infinity would be?
Infinity.
And now, what do you guys think about negative infinity? Take away infinity.
Positive? No.
If something's already at negative infinity, and you make it go negative infinity even more, it's just negative infinity. Okay. Now this one, I don't want you to write this one yet, but this doesn't have an answer. If you take infinity away from infinity, you might be tempted to say 0, but you're assuming the infinities are the same size. That they're not. There's different infinities, so we can't say that. So don't write that one. That's actually what we call an indeterminate form, and that's going to be one of your extra credit lessons that I put up for you guys to do. You can use L'Hopital to deal with those, but that's actually an indeterminate form. But all this stuff is pretty straightforward here. Or Linda.
Here you go.
You're so sweet. Thank you, honey. You guys know her, right? The burrito girl. Got another. Her Linda. But she's like famous on campus for her burritos.
Mr. Johnson does it too.
I know he does. All right, here we go. So let's go ahead and do an example here to put this to work for us here a little bit. Example 1.
So does she like sell burritos?
Yeah.
Okay.
$5.
How much?
$5.
Oh,
Can you get yours before you assuming?
This one was
she take on.
because I wouldn't. I try not to break food, but that was true.
You just recorded that.
But I try not to break food. What are they gonna do, Your Honor? He tries not to break rules. Throw him in jail. All right, got a burrito for free. All right, here we go. Now, what's 5 going to be as x approaches infinity? No, it's just going to be 5. Okay. Here's the line y equals 5, right? And as x goes to infinity, the y value never changes. It's just 5. So at infinity, y is 5. How about here? We're going to plug this in. We get -3 times infinity squared. Now, what's infinity squared? And what's -3, I should say, times infinity? And what's 5 take away infinity?
Negative infinity.
There's your answer.
Okay, wait, that was really fast.
I could go slower. So how about this? I want you guys to find the limit as x approaches infinity for this following expression. Go ahead. Go ahead. Somebody to help me out here. I gotta. Sure, Pearl. What's the answer? The answer is infinity, because if you plug in infinity here and you square it, you get infinity, and infinity times 4 is still infinity. And if you plug in infinity here and multiply it by 5, you still get infinity. And then we're subtracting 10. Now, infinity plus infinity is just infinity. And if you take 10 away from infinity, it's still infinity because it's got infinitely much to give. Kind of like the amount of love in my heart.
Oh, brother. Oh, brother.
I don't know what's wrong with me, but I enjoy it. So here we go. Let's continue. I said what I said.
That was good.
Okay. Next one, ready? B. Division properties with infinity. Okay, division properties with infinity. So first of all, what do you get if you take infinity and you divide it by a number? Infinity. That's true whether it's positive or negative. So if you have positive infinity and you divide it by a number, you get positive infinity. If you have negative infinity, you divide it by a number, you get negative infinity. No big whoop there. All right, how about this? This one is not so obvious. What do you get if you take a number, positive or negative, and divide it by infinity?
The number is just a number. C. Zero.
We talked about this. Remember, when you divide by bigger and bigger numbers, what happens to the fraction? And as it goes to infinity, it goes away. So the answer to this will always be 0. Doesn't matter whether it was positive or negative to begin with. All right, now this one is not obvious, but I don't know. We'll see how you guys do with it. What happens if you take C and now you can't divide by 0, okay? And I want you guys to understand the reason why they don't write math like this is because it makes it look, sorry, I got an itch. Anyway, the reason why they don't write it like this is because it makes it look like that number's just chilling there and you're treating it like a normal number, but it's not a number. This is something we're approaching, okay? So when I put 0 here, I don't mean we're plugging in 0. You can't do that. We're approaching 0. So when you look at this, I want you guys to think, what happens to a fraction when you divide by a number that's smaller and then smaller and then smaller? The fraction gets bigger. It's actually the opposite of this one. So when you divide by something that gets bigger and bigger and bigger and bigger, it approaches 0. But when you divide by something that's smaller and smaller and smaller and smaller, the fraction gets bigger. I mean, case in point. So the answer here, by the way, would be infinity, plus or minus. It just gets bigger and bigger forever. So here's a case in point. What do you get if you divide 1 by 1? You get 1. What do you get if you divide 1 by 0.1? You get 10. How about 0.01? 100. So the smaller that number gets, the bigger the fraction becomes, right? And so if you divide by something infinitely small, you get something infinitely big. Okay? So these are kind of like inverses of each other. Dividing by something super big makes 0. Dividing by something super small makes infinity. So let's go ahead and pull a couple of these together for us. Example 2. Limit as x approaches 1 for 2 ln of x over x minus 1. I know. Very cool. All right. So first of all, let's do some direct substitution, shall we?
Wait.
What do I get on the bottom?
0.
What do I get on the top?
2.
Shame.
0.
It's 0. Because ln of 1 is 0, and 0 times 2 is 0. So we get 0. What does that mean? That's L'Hopital. Okay? So let's do L'Hopital. All right, so this is going to be 2, 1 over x over, what's the bottom going to be? 1. Just take the derivative of the top and bottom, right? Now let's do our direct substitution. What's my answer going to be? 2. Oh, that wasn't even an infinity question. That was kind of boring.
Wait. Okay, wait, I'm confused. We went from 2 ln x over x minus 1. You plug in the 1. Then there's 2 ln times 1 and 1 minus 1 is like what? 2 ln on the top?
Or then, we'll call this A. Let me do one that actually does apply. B, let's do the limit as x approaches infinity for x over 2. What would it be? It would be infinity, because you have infinity divided by 2, which is infinity. Now I'm going to give you guys 2 to try. Ready? The limit as x approaches infinity for 2 over x, and then I want you guys to do the limit as x approaches 0 for 2 over x. Go. You guys have C and D. Go. Okay, here we go. Mateo! Mateo!
Yeah.
What'd you get for C?
C at 0.
I agree with you.
Are you sure?
Yes, 2 over infinity is 0 because you're dividing by something infinitely large. Tristan, what did you get for D? Or Ryan, Tristan, huh?
Infinity.
Infinity, because you're dividing by 0. In other words, you're approaching 0. You're not really dividing by 0. You're approaching 0, which means you're dividing by something infinitely small, which makes the fraction infinitely large. Well, okay, so the reason I had that on that last slide was I want you to be aware that the sign matters. So like if you're dividing a positive c by 0, then you get a positive infinity. But if you're dividing by a negative c, you get negative infinity. All right. Good question. All right, now we're going to talk about trig functions a little bit. But we're not plugging in numbers really today. We're plugging in infinity, so you guys don't got to worry about your unit circle too much. All right, so you guys know what cosine looks like and sine? They look like this, don't they? How about secant and cosecant? You guys remember they look like this? And do you guys remember that tangent and cotangent kind of look something like this? Okay, so if I were to ask you guys, what is the limit of these functions at infinity? It doesn't have an answer because it's not reaching anything. It's just bouncing back and forth. Whether you're doing this one or this one, they just keep going up and down forever, right? So we call that oscillating. Oscillating means just pendulum swinging, going back and forth. So let's go ahead and write down C, limit properties with trig. Okay, so here's the first thing I want you guys to know about limit properties with trig. The limit, as x approaches either positive or negative infinity, it doesn't matter whether you're moving left or right, of any trig function. So I'm just going to put the word trig here. This is bad math writing, just so you know. Okay, this is just for notes. The limit of any trig function as I approach left and right forever does not exist because they oscillate. You never reach anything at infinity. You don't reach anything specifically at infinity because they're constantly just going up and down. Okay, they oscillate. So let's talk about some other things here. What happens if you have a trig function? I guess we could probably have a few of these things. What do you guys think would happen if you took a limit and you ended up getting infinity times a trig function, which I'm just going to say is oscillating? Yeah, it does not exist. Why doesn't it exist? Because it's not necessarily going up to infinity, right? The reason is because it's going up and down to infinity. So it's not reaching anything. So we're going to say it oscillates. And we're going to say, therefore, it does not exist. Okay? It does the same thing on both ends. Yeah, they're symmetrical like that. But when you're talking about limits, you're talking about y values. And so it's oscillating up and down. And so since it's not reaching if it were only going up, you could say infinity. But it's not. It's going up and down. So we can't say it exists. All right. What if you took infinity and you divided it by a number that was just going up and down? This is a little less obvious. So let's say your top of your fraction is getting bigger and bigger and bigger, right? The bottom, it's just kind of going back and forth between 1 and -1 repeatedly, like sine and cosine do. What would happen? It wouldn't exist again. So even though this function is trying to go up, the problem is every time you divide by a negative, it drops it down to negative, and then it goes back up and then down, boom, boom. It's trying to grow, but this division and the constant changing of the sign is pulling it in different directions, so it can't keep growing. It gets confused. So once again, we're going to say it does not exist. It oscillates. Okay. What if we switched it, though? Let's say we had an oscillation going on the top, but we divided by infinity. So you have a function that's doing this, bouncing back and forth between 1 and -1, but your bottom of your fraction is getting bigger and bigger and bigger. Huh? It exists. It's 0. Let me show you what happens here. The top is causing this function to do this, right? But because you're dividing by bigger and bigger numbers, it flattens it out. Does that make sense? It causes that height to decrease repeatedly. So yeah, it looks like a heartbeat kind of. It causes it to mellow out. So for this one, oops, I didn't want to do that. For this one, the answer we're looking for then is 0. Okay, so let's go ahead and put this to work for us. So a lot of times trig functions just cause it to not exist because trig functions oscillate. But in the case where you have an oscillation in the numerator and infinity in the denominator, then you're going to get 0, okay? So let's go ahead and try a couple of these. Example 3. Oh, poo. X over sine of negative 3x. And I need to take the limit of this as x approaches infinity. Okay, so if I plug infinity in the top, what am I going to get? Infinity. If I plug infinity in here, that's sine of infinity. And what does sine do at infinity? It wiggles. So, but by the way, when I plug this in, the infinity becomes what? Negative infinity. But it doesn't really matter because sine does the same thing on the left as it does on the right. It oscillates. So, and once again, I want to emphasize, this is bad math writing. You would never write stuff like this on FRQ. This is just for quick answers to like multiple choice questions, okay? If on FRQ, you could do this stuff, but then scribble it out and just put your final answer because you don't really need to show work on these because like Jonathan demonstrated earlier, you can really just look at them and know the answer. I'm just showing my work to help your notes make sense. But just remember, this is all bad math writing. All right, what's infinity over an oscillation?
It does not exist.
It does not exist because it oscillates. It doesn't reach anything. All right, so there's that. Let's do another one. How about the limit as x approaches negative infinity for x cosine of 1 over x? I wonder if this is a good idea. I think this will work. Okay, I think we're good. Okay. Yeah. That was oscillation. That was 0. Okay, here we go. So if I plug in here, what do I get? You get negative infinity. Now, if you plug in here, you get 1 divided by negative infinity. Now, I'm gonna write this. But what is 1 over infinity? Any number over infinity is 0, right? So what is cosine of 0? It's 1. And what's 1 times negative infinity? There you go. Okay, so I lied. You do got to know a little bit of your trig. Probably 0 would probably be it, or something like that. All right, so I'm going to throw a couple of these at you. They involve oscillations, and that's it. So there's so many we can do, though. I want to see what you guys are capable of. I don't know. I'm going to give you a lot. Okay? I'm going to pause my video. I'm going to write them all. Give you a little bit of time on each one. All right, let me find this stuff here. Okay, go ahead and do that one. I'll give you a few seconds. If you don't, write down as many of these as you want. You don't have to write down them. I mean, if it's just really obvious to you, then you're fine. If you see one that you think, I don't know that one, you better write it down. This is, yeah, we're just going to do a lot of student practice now, and then we'll probably call it a day here pretty soon. But we're going to do a couple problems at least, make sure you guys got the idea. Answer for this one is does not exist. Direct substitution, which is technically illegal because you're not allowed to plug in infinity because it's not a number, but we're going to do it anyway because we're rebels, gives you cosine of infinity. And all that means is what is cosine doing at the right forever? It's wiggling. And so the answer is does not exist. Okay, let's do another one here. Try that one. So if we do direct substitution here, you get oscillation. Here, you get infinity. Oscillation over infinity is 0, and the limit of a constant at infinity is still 2. So the answer is 2. Okay? Another one. Make me proud. Napping, but I have faith in you. What do you think? Infinity over oscillate. You had a 50-50 on that one. It does not exist. It oscillates. Because what you get here is you have infinity over an oscillation, and that would be does not exist. All right. One more. We've already done one like that. I don't know. I want to find something different. We've already done that. This one looks promising. Okay, let's do this one.
Oh my god.
Okay. How about Andrew? What did you get?
So, first part, that's the bottom part.
It's not oscillate. Well, it is, but it reaches a limit. It reaches a limit. Let's see, Zarina, what do you think? Yeah. It's negative infinity. So let's see why. Check it out. So if you do your direct substitution, you end up with cosine of 1 over infinity. And what's cosine of 1 over infinity? That's going to be cosine of 0. And what's cosine of 0? So this denominator is basically 1. Okay? So the bottom becomes 1. Now let's do the top. If you plug in infinity to this, you get 3 times infinity, which is infinity. Now what's negative infinity divided by 1? There you go. All right, so we're good now. As you guys already know, you don't need to write these, but we've talked a lot about these little representations and what they mean. We've already talked about these ones too. These are indeterminate, right? So when you have those, you use L'Hopital. The limit may exist or it may not. It's indeterminate because you just can't determine. So L'Hopital helps us figure that out. There are other indeterminate forms that L'Hopital can't work for until we make it work for L'Hopital. So for instance, this is another indeterminate form. And I told you about this one as well earlier today. That's also indeterminate. And there's a whole bunch that have powers involved, like this. That's indeterminate. I believe infinity to the 0 is indeterminate. And I believe that 1 to the infinity is another one. These three kind of all go together. This is what your extra credit homework video is all about. How do you deal with these? The trick is the idea is the same on all three. Somehow we need them to turn out to be like these guys up here. So what we do is we do a bunch of algebra tricks to massage them to look like this so we can do L'Hopital on it. That's the idea. This one is really easy. The other two are like my first year teaching calculus. I just thought, yeah, they'll get this, and I started, and then halfway through, I thought, I need to stop. I'm gonna kill somebody. It's very intense algebra. It's not bad. It's just you have to be ready for problems that will take a page. But it's extra credit, and I'll throw a few on your test too. Okay. I don't know when I'll make the video. I'll try. If I don't get to it today, I might have to do it next week sometime. But anyway, so there's extra credit videos for this, and I've already put one extra credit video up right on the squeeze theorem, I think is what it's called. That's a really easy one. Don't skip that. It's kind of pointless. You would probably not even see an AP question on the squeeze theorem. However, ironically, the first time I've ever seen one was last year, the FRQ. So I actually included that in your practice exercise for that extra credit. But it's very rare to see anything with the squeeze theorem. It's kind of a theorem. Yeah.
So when you put this on the test, will it be extra